Welcome to our coverage of the t-statistic. We're going to introduce this today, and then we'll spend another couple lectures here. But this is a voyage onward as we leave the familiar ground of Z territory, and we'll find out, why do we need t? Z seemed just fine for a lot of our needs. Well, we'll find out that, yes, if all things are equal, we choose the Z statistic, but real life doesn't give us some of the things that a Z statistic requires, so then we have to have an alternative, and not surprisingly, that is the T statistic. Here is an overview of what we'll be covering today. Compared to the last discussion we've had, which included tons of new things, this is basically introducing all of those things again around this slightly different, but should be mostly familiar T statistic. But first, let's start with a review from what we covered last in hypothesis testing. First, what do we mean by the standard error of the mean? This is essentially the level of variability around the middle of our distribution of means, or our sampling distribution. Again, SCM, or the standard error, is like a standard deviation of individual scores, but it's just a standard deviation of means, so we call it a standard error. What two things have a large influence on the standard error? We'll go back to the equation. The top, which is the population standard deviation, if that is big, the top of an equation is big, then the result will be big. If it's small, the result will be smaller. Then we also look at the bottom of our standard error equation, which is the radical n size, which means take something and divide it by a big thing, you get a smaller thing. So big sample size gives us a smaller standard error, and large sample size, small sample size gives us a larger standard error. So the two things, the numerator and the denominator of our standard error equation, are the two things that influence the resulting standard error: the population standard deviation and the sample size. What is alpha? Alpha is often referred to as our, well, I guess our first official definition is basically the area of our distribution, our null distribution, that our sample mean needs to fall into for us to reject the null hypothesis. Alpha also is related to our type 1 and type 2 error, which we'll get into, specifically type 1 in the next bullet point. But common alpha values are alpha of 0.05, 0.01, and 0.001, or that corresponds to 5% of the area of the distribution, 1% of the area of the null distribution, or even 0.1%. Also, what is type 1 and type 2 error? Type 1 is mostly related to our alpha. It's the chance that we reject the null, that sample mean falls into our critical region, but maybe it was just due to sampling error. Maybe it's not reflective of a real effect in the larger population. What is type 2 error? It's the opposite. It's failing to make a decision, failing to reject the null, when actually there is an effect. And how are they different? Well, they're kind of the exact opposite. You know you have a chance of making an error in this decision game, just like any decisions in life. Do you want to make a type, would you rather make a type 1 error and claim that something's there when you have to run it back and say, I guess I was wrong? Or is it failing to say that something was real and then proving later on that it was real? That's the type 2. And if you guard against one, you are opening yourself up more to the other. If you guard against the other, you're opening up yourself more toward the first one. So it's kind of like decisions in sports. Do you want to be aggressive and make a mistake? Are you okay trying to be aggressive knowing you might make a turnover? The turnover would be a type 1 type of error. Or are you going to play really conservative? The last thing you want to do is have a turnover. The last thing you want to do is make that mistake. So you'll make other mistakes, such as being predictable in play calling or not aggressive, just so you don't make that one big mistake like committing the turnover. And continuing our hypothesis testing review, what is the idea behind power? Power involves the number of decisions we can make in setting up our null distribution and process that will make it more likely for us to reject the null hypothesis. Which type of error does it guard against? The more power we have, the more likely we are to make a type 1 error. We're more likely to jump the gun and conclude that something's there, and then maybe later we have to walk it back and admit that it wasn't. So you're allowing yourself the possibility of making a type 1 error because you don't want to make a type 2 error, which is if you want a ton of power, you're doing that so you don't miss anything that's potentially there. You don't want to have too high of a standard so that you miss something, but you have a low enough standard that you might think you see something that actually isn't there. So you make the type 1 error, but you're guarding against the type 2. And if you, for example, then have lower power, you will have a lower chances of making a type 1 error, but then you open yourself up to a higher type 2. Raise the standard, lower the power, and you might just not be able to make a conclusion about something that maybe a less strict standard of evidence would say is actually there. So what are the 4 main influences on power? We won't go through all of those right now, but think about you can have a directional test, you can have a larger alpha, for example, you can have a bigger effect. All those things will give you more statistical power. And then finally, what does it mean to be statistically significant? It means that we've seen enough that we can conclude to reject the null hypothesis that there is a significant difference or there's a significant effect. It doesn't mean that it's big, that's effect size. It's saying that it's real, it's there, and then if we want to know how big is it, then we go to effect size. Then finally, what do these symbols mean? We have our alpha level, our chance of making a type 1 error. We have our beta, our chance of making a type 2 error. And then D reflects the effect size. How big is the effects of what we're looking at, regardless of the cheat code that can be a huge sample size. Now let's introduce the t-statistic. The best way to introduce the t-statistic is to compare how different it is and similar to it is from our z-test or our z-statistic. So we see for our z, we just have a sample mean, and from that we subtract the population mean over the standard error. What might be the problem? Well, a lot of times we don't know this standard deviation for the population. If we don't have the standard deviation, we can't plug it into a formula for standard error. So if we don't know the population variability of our distribution of means or our standard error, what are we supposed to do then? Well, what we're going to do is estimate this property from our sample data. So once again, for our z, our comfortable z statistic, we know our population mean, we know our population standard deviation, and we can use that to calculate our standard error and ultimately our z-test or z-statistic. So thinking about the z-test logic, again, just explaining in words what's right there in the formula. And then finally, continuing that, we have our null distribution. We've decided what alpha level to use. We've decided whether it's a 1 or 2-tailed test. And then, depending on what our z is, whatever it is, we put it on that null distribution. And if it falls in the critical region, if it's unlikely that it fell there just due to chance, we say our z, our sample, was a treatment mean, and you can't put it on the null distribution because it's significantly different, there's a significant effect, then we reject the null hypothesis. How is the t-statistic different? Well, let's find out. Here's an example. If we want to know whether psychology student GPAs are higher than the BGSU average. So we might know the BGSU average, but not the variance or the standard deviation. In that case, we'd like to use Z, but it's now no longer an option. What are our hypotheses in this case? Well, let's say our null hypothesis is, notice we are saying student GPAs are higher than. So psych student GPAs are greater than BGSU average. We're looking at a one-tailed hypothesis. We're not saying different from, we're saying higher than. So we're saying we think we know which direction that's going to go. So the null hypothesis is that the psych GPA is not higher than the BGSU average. And then our null hypothesis, or excuse me, alternative hypothesis is that the psych student GPA is higher than or greater than the BGSU average. So how do we go about estimating our denominator or our error? Well, first of all, we can look at how do we get to our population standard error of measurement. So here we have the equation for that. What does the estimated standard error look like if we don't have that population standard deviation? Here is where we are doing a little cheat code, and we'll find out later that it's largely supported by mathematical theory, but we take our sample standard deviation and everything else is exactly the same compared to our population standard error. Now, if you see this S, this is again dealing with our sample standard deviation, or if it's in the square term, sample variance. And then the resulting number we get is what we call our estimated standard error. So essentially, we're just taking this standard error estimate from how we do it with the population values known. So the same thing applies in terms of our Z formula, our Z test becoming now the same numerator. That hasn't changed, but now we just have T uses our estimated standard error in the denominator. So really, that's all that's different. One thing to consider that is kind of interesting is that unlike Z, which the distribution for the unit normal table, they generally looks the same. Depending, and it can get squished up in the middle or really stretched out depending on the population standard deviation, but the T distribution changes even more. And what that means is exact properties of a T distribution depend on the degrees of freedom. Degrees of freedom is, in this case, with one sample, n minus 1. And you can see that the sample size is going to come into play on how the T distribution looks like. So why do we use degrees of freedom? That should be a Y. Well, it's because when we do that estimation, we lose a degree of freedom. So the other ones have to be set because we're just taking one value and estimating it. So in this case, the standard error for our Z distribution is constant, but the estimated standard error is not. Estimated standard error can vary from sample to sample, which we'll be able to see in the next slide visually. So what this means is we have our normal distribution, which is this dotted line, and we see a T distribution of a degree of freedom of 20. So if that was n minus 1, what was the sample size? 21, n minus 1 degrees of freedom of 20. And we see it's different in terms of the peak is lower, and then it's a little bit chunkier on the outside edges or the outlying areas. And the smaller the sample size, the more exaggerated this difference from normal distribution becomes. So that means how we find our critical areas and values, our cutoffs, is going to be a bit different. We have to factor in the sample size when we didn't have to do that looking for critical regions for our Z table or unit normal table. So essentially, The greater the degrees of freedom, the closer the t-distribution is to z, and those cutoffs will look about similar to some we've seen before. And it usually, so it can go up to infinity, but once you get past 200, the t-distribution is essentially the same as z. But if we're dealing with smaller sample sizes, it makes a bigger difference on the types of critical values, as we'll see, that we'll have to use. So now let's look at the t-statistic in terms of how we do hypothesis testing, and we're going to find out it's pretty similar to the z-statistic that we've covered previously. Now that we're moving from the z-table that we learned the last couple discussions and hopefully got comfortable using, now we're into t-land, and because the t-distribution looks different based on the degrees of freedom, we see that the table looks different. So in one thing to think about, we have, for example, our degrees of freedom, and this is just a short version. You can see the full table as a handout I'll make available in PDF and also at the back of your book. Now also, you can see a couple different choices you have: proportion in one tail, and unlike the z-table where we could pick our probability, if we wanted to find a probability of 0.125, we could find it. Here, we're stuck with the values they give us. So now we see some common alpha values, 0.05, 0.01, and then we see proportion and two tails combined. So one-tailed test here, two-tailed test here, and then we find our degrees of freedom, and we can find a cutoff value. For example, two tails combined, our cutoff score for a sample size of n-1 equals 5, so a sample size of 6. And notice, that's a lot higher than our just maybe 2 standard deviations above the mean, z-score of 2 on our z-table. And that is because, especially at lower sample sizes, the t-distribution looks a lot different from the z-distribution, and so the cutoff values, critical values, for the same proportion in t are higher than they are for z. So for example, given these parameters, alpha of 0.05, two-tailed test, degrees of freedom of 15, so it would be a sample size of 16, we see the cutoff values here. So notice, compared to the last one, two-tailed alpha 0.05, we were looking at a t of 2.5 plus or minus. Now moving from a sample size of 6 to a sample size of 16, our critical value looks a lot lower. So even at a sample size of 16, now we are closer to critical values similar to the general 2 standard deviations above the mean in our z distribution. So let's look at the basic steps of doing a hypothesis test with our t-statistic. First, we state our hypotheses, determine the alpha level, choose whether it's a one or two-tailed test. And of course, that should be based on how you phrased your hypotheses, equal to or greater than or less than. Determine the degrees of freedom, so that's an extra step compared to before with z. And then find the cutoff in the z-table. And then we calculate our t-score. And again, our formula is fairly simple. We just have our mean difference, or our effect on the numerator. And then we have our error term, or our kind of our noise here. And to make this difference look big on top, we would like this error on the bottom to be small to give us a bigger t-statistic. So hopefully you can start seeing that in the equations. What leads to getting a t-statistic that is more likely to lead to the null hypothesis being rejected? And then finally, that leads into our actual decision, deciding whether to reject the null hypothesis. So let's look at a logic. Let's look at an example here. We want to know if a training program has an effect on employee performance. And notice we're saying has an effect on. So we are looking at a two-tailed test rather than a one-tailed. We're not saying training program makes performance better. And it's important to consider. We like to think our training is going to improve performance, but if we're not absolutely sure, we have to allow for the chance that it might actually make performance worse. So in this case, we do have a population value, mean of 25, but we don't have that population standard deviation anymore. So now we're going to have to use our sample standard deviation to get our estimated standard error. So what are our hypotheses? Basically, our null will say that training program performance for employees is equal to trained and untrained. They're the same, no difference. And then the alternative hypothesis will be phrased something along the lines of employee training performance will be greater for trained employees than untrained employees. There will be a mean difference, so we'll use that not equal sign. No greater than or less than, because we're making a two-tailed or a non-directional hypothesis. Given those stats from the previous slides, we need to set our decision criteria. Let's maybe just go with the default alpha of 0.05, two-tailed. And here we go with degrees of freedom, n minus 1. We see our n size is 16, so our degrees of freedom should be 15. And then what is our critical value? For that, we would need to look at our t-table, but we'll work through it here in a little bit. So what does our t-statistic look like? Well, we need to find the estimated standard error. So we need to pop this into our formula. So how does this work? Now notice the equivalent of this equation is also just take the square root of both of them, and then you would just have s over radical n. You can use either formula, but from this number, I think I'd rather just have that 6 on top. So I'm going to take the square root of both. So the equivalent equation is s over radical n. So I'm going to take 6 over radical 16, which is 4. So 6 over 4 is our estimated standard error, which should be 1.5. We plug that into our t formula. And what is our mean difference? Well, we would have, for example, 33 sample mean minus population mean 25. So we would have 8 divided by 1.5. Let's think about what that might be. And then we get our t-statistic of 5.33. So let's say this was the cutoff value that we found in our t-table for alpha 0.05 in two tails, degrees of freedom of 15. So our t would have to be lower than negative 2.1 or higher than positive 2.1 for us to reject the null. And clearly we see it is higher than our cutoff values. It is in our critical region. And then we reject the null. We say that we reject the hypothesis that there's no difference, that the training didn't make an effect. And then we say the alternative says there was one. That's what we're going to go with. Haven't proved it completely, but we've provided evidence that the null was not the one to go with. And of course, now we're in significance testing. We want to do the significance test, get our yes or no answer, effect, or is there something real or not? The next question is, how big is it? How big is the effect? So in this case, the effect size for the t-statistic has a couple different options. And once again, the significance doesn't tell us how big the effect is. It just says whether it's there or not. And of course, a big effect is more likely to be significant, but you can get significance of small effects if you just have giant sample sizes. So first of all, Cohen's d, similar to what we use with our z statistic, is just the mean difference over our sample standard deviation. Again, we're taking out that divide by the sample size to standard error and just sticking with standard deviation that doesn't have that bias for big sample sizes. So what is the effect size for our training example? Well, we have our mean difference, once again, is 33 minus 25, 8, over our sample standard deviation. And so 8 over 6, we clearly see that is over 1, and we would conclude that that is a large effect. Now, we can also think about variance accounted for. And we'll talk about R squared later on, specifically once we get to correlations. In fact, R by itself does stand for the correlation, and then R squared is variance accounted for. And we can, this is a formula that I just wanted to introduce because you might see it other places, but basically we're not going to be using it. We'll stick with Cohen's d for the effect size. But notice that you can just take the t-statistic and square it, and then over t squared plus the degrees of freedom to get the amount of variability in employee performance that's explained by the treatment. And in that case, it's more like a ratio. You have a certain amount of variability of training performance or job performance. What percentage of that is explained by the treatment? So you can only get up to 1 when we're talking about variance accounted for. You can't explain more variance than exists, for example. So we can pop those numbers in if we wanted to, but again, we're not going to be using this formula moving forward. Just wanted to introduce you to it if you see it in the future. Also, we have our effect size guide, and similar to the guidelines that we were using before with our Z statistic, we're just going to go with those same guidelines. If it's approaching 1 or larger, we know it's a large effect. 0.2 or lower, small effect, and anything in between is generally a medium effect. And the final thing we'll cover is a directional hypothesis with these t-statistic. So here we see maybe we want to change our alternative hypothesis when we started this test to saying we're pretty sure the training's not going to cause a decrease in performance. So we want to increase the power of our statistical test, put all of that critical area into one side, and notice what happens. When you combine the two tails into one, instead of being the cutoff of 2 point something, now our cutoff is lower. This lower cutoff represents the higher power of the one-tailed test. And notice our hypotheses have changed in terms of our phrasing to say the old alternative hypothesis said training has an effect on, and now we're saying training improves. And again, our t was positive, so we would still reject the null hypothesis in this case. So hopefully that makes a lot of sense and isn't too many new things compared to what we did in previous slides or previous lectures, because a lot of what we're going to be doing moving forward is just working with different kinds of situations, different kinds of data, but the basic logic of the hypothesis test, if you understand type 1, type 2 errors, phrasing the different hypotheses, you're in good shape moving forward. So looking to build on this in the future.